Part B, problem B2, second problem of two problems in this section. Consider a parallel plate capacitor with the plates vertical. The plates of the capacitor are rigidly supported in space. The distance between the plates is d small. The plates have a height h and area A big, much greater than d square. Assume throughout this problem that the force of air resistance may be neglected. However, the force of gravity cannot be neglected. Neglect any H effects as well as any magnetic effects. Section A. A small metal ball with a mass big M and a charge Q is suspended from a string of length L that is tied to a rigid support. When the capacitor is not charged, the metal ball is located at the center of the capacitor at distance d over 2 from both plates and at a height h over 2 above the bottom edge of the plates. If instead a constant potential difference V0 is applied across the plates, the string will make an angle θ0 to the vertical when the metal ball is in equilibrium. First, determine θ0 in terms of the given quantities and the fundamental constants. Second, the metal ball is then lifted until it makes an angle θ to the vertical, where θ is only slightly greater than θ0. The metal ball is then released from rest. Show that the resulting motion is a simple harmonic motion and find the period of the oscillations in terms of the given quantities and the fundamental constants. Third, when the ball is at rest in the equilibrium position Q0, the string is cut. What is the maximum value for V0 so that the ball will not hit one of the plates before exiting? Express your answer in terms of the given quantities and the fundamental constants. First, let's draw the picture showing forces acting on this ball. So we have mg, which is a force of gravity, vertical force, and we have force horizontal, Q multiplied by V0 divided by D, where V0 over D, that's the electric field, and field multiplied by charge, that's a force. So from this picture we can immediately find that tangent θ0 equal this expression, QV0 over dmg. That's the answer for the first question. Second question. The metal ball is then lifted until it makes an angle θ to the vertical, where θ is only slightly greater than θ0. The metal ball is then released from rest. Show that the resulting motion is a simple harmonic motion and find the period of the oscillations in terms of the given quantities and the fundamental constants. So first of all, if we apply additionally to gravity force electric force, we have a new force and the angle θ0 acting on this ball, and we can assume that this new net force acting like a new gravity force, and we can find g prime gravity acceleration for this force. Force could be found from this equation. This is just pure geometry because both forces are perpendicular to each other, and effective gravity acceleration for this case equal G prime equal force divided by mass, which is this expression. And last thing is we can find what is a period for pendulum with length L and gravity acceleration of free fall. In our case it's a G prime. Period will be 2 pi L over G prime, and now we can substitute a G prime here and find what is total period. So period will be this expression, 2 pi and root 4 from L square over G square plus Q V0 over dm square. So that's done. So we can write this answer in form of this one, or better this one. So that's the answer for question 2. Question 3. When the ball is at rest in the equilibrium position theta 0, the string is cut. What is the maximum value for V0 so that the ball will not hit one of the plates before exiting? Express your answer in terms of the given quantities and the fundamental constants. So first let's draw this picture. We have on this picture we have angle theta 0 between the vertical and the direction of string, and we see that if this tangent of this angle exceeds d over 2 divided by L plus h over 2, this ball will hit this plate. So it means that we have to make this inequality. So tangent theta must be less than d over 2 divided by L plus h over 2. But tangent theta we already counted, this one. And after we insert this tangent, we can get this inequality. So it means that V0 must be less than this expression. That's the answer for third question. Question B. Suppose instead that the ball of mass m and the charge q is released from rest at a point halfway between the plates at a time t equals 0. Now AC potential difference V as a function of t equal V0 sine omega t is also placed across the capacitor. The ball may hit one of the plates before it falls under the influence of gravity out of the region between the plates. If V0 is sufficiently large, this will only occur for some range of an angular frequency omega minimum less than omega maximum. You may assume that omega minimum much less than square root from g over h, and omega maximum much greater than square root from g over h. Making these assumptions, find expressions for omega minimum and omega maximum in terms of the given quantities and or fundamental constants. Solution. We have potential difference as a function of time. It means that we can count what is the horizontal force on this ball, and by integrating we can find what is speed, and after that what is displacement, horizontal displacement. So first of all we can write expression for acceleration. This is our acceleration. That's force q v0 over d divided by mass. and multiply it by sine omega t. First we can integrate this formula to find what is formula for speed. That will be this one. Here we use knowledge that the initial speed is 0. It means that cosine omega t is 1 and the total is 0. This is how to find constant for integration. Second, we can integrate this formula again and find what is horizontal displacement. That will be this one. Again, when time equal 0, we have displacement is 0. Now let's count what is time to travel, because we have free fall in the vertical direction, and we have this formula, and time will be total time to travel. So now let's examine our conditions. First condition, when omega is much larger than this expression, it means that period will be much less than total time to travel. It means that in this formula 1 over omega will be much less than total final time, and we can neglect this member, and we can leave only time t here and neglect the right expression. So we have, and we have total distance is this one, and now we can estimate that this distance must be less than d over 2. We have d over 2 greater than this expression on the right side, and from this inequality we can find what is our omega, which must be greater than something. In that case we have omega, if omega greater than this expression, which we can call omega maximum, this ball will never hit the plate, but if it's less, that will hit this plate. Let's count other possibility when omega is very small. If omega is very small, it means that this sign could be represented in this form. So for small omega t, we have this approximate expression for sine omega t. We will get this expression for x, and now we can put here expression for time, and we have for displacement we have this expression. But if we don't want to hit this plate, x must be less than d over 2. It means that we have this inequality, and finally we can find that omega must be less than omega minimum, which is this one. So we found that if omega less than this expression, which we can call omega minimum, we will not hit this plate. So that's the answer for question B.